of the magnetism folder, what I have done for you is I will put in the assignments, but you do have this magnetism quiz that's due on the 23rd. And then I have actually gone through and have given you the lectures that I have, like, and if you follow these in order, these will give you, as we go through the various things for magnetism. And so you do have a lot of material there. So magnetism is kind of an interesting item, but I do want to show you a few things. One is here is the Earth's magnetic field. And the Earth's magnetic field is constantly changing and is looking at how we rotate. So you've got a nice article here about the Earth's magnetic field. And we are a dynamic planet, so we do have things that impact our magnetic field. Oops, it just kind of clicked it again. But you have got the various items here, so you can go what causes our magnetic field, but it's the protection of the magnetic field that actually causes our auroras that we see, the aurora borealis or the aurora australis. And that also protects us from items from the sun. And if you've been following science news this last week, you'll have noticed that we've had a space probe that actually went through and saw a lot of different things that are out there on the sun. So we have a lot of good things associated with it. We do every now and then, we will have our magnetic field will flip, and we have that flip. We see that every 200 to 300,000 years. We kind of are a little overdue for the flip. So we're watching our magnetic field kind of great at the moment because we're watching changes because we're expecting it to flip at some point in time. So you do have that kind of information about the Earth's magnetic field. So it's really interesting, and we can follow it in the geologic record to be able to see that. Okay, maybe. There we go.
What exactly do you mean by flip?
Our poles, so instead of what we consider magnetic north being our north pole and our magnetic south being our south pole, periodically it's like the bar magnet flips over.
That makes
And most of us don't know, we see it in the logic record, because if you follow granite and you've got the iron in the granite, it will actually orient and you can actually see it. And so we know that it has flipped, but nobody knows exactly what happens when it flips. So we're all kind of watching it, just to see what happens. Apparently it hasn't done too many things for us, but that's one of the things that we do look at it. When we get to AC current, you'll see AC current in here, and we'll talk about the three phase and all of that, but we'll get to early on. And then you got under the demonstrations of the magnetic fields, maybe it's going to take a little bit. It's thinking about it. All right. Okay, and when you go under, oh, there we go. I knew there was more stuff in here. You do have extra problems and other demonstrations. This one, I encourage everybody to watch, the levitating barbecue from Vertasium. It is a really good one, and it explains a lot about the induction and Maxwell and Faraday. There's one other one I wanted to make sure everybody could find, and I'm not seeing it. You've got the magnetic field between two current wires. You have lots of homework problems here for the magnetic field. It's thinking about it again. Let's see if it will actually open up for me. All right, in here, I have demonstration of a couple of actual setup laboratory demonstrations. So in here, you can actually measure a magnetic field. What we're going to see is that Ampere made an observation. And I have a U-shaped horseshoe magnet. I've got two clothespins, and all the clothespins are doing is just holding the magnet upright so that we've got our magnetic field that's generated by our magnet. You can see the weight of the magnet plus the weight or the mass of the magnet plus the mass of the clothespins. And I've got a wire. And over here, you can actually see that right now there's no current going through the wire. And as Ampere demonstrated is that once I generate a current in the wire, a wire is going to generate a magnetic field. And you can see this a couple of different ways. One is you can put a compass there and you can actually see the compass needle move as you approach it to a wire. And we can actually see it here because we know that if I have two north poles of my magnets together, they're going to repel. If I have two south poles, they're going to repel. But if I have a north and a south pole, they're going to attract. And so what we've got this set up so that if depending on, and I actually have it set up so that the magnetic fields are going to repel. And as I increase the current and generate a bigger magnetic field around my wire, it's actually going to push down on the my magnet, and we can actually measure the force. So I'm going to go ahead. Yep, I got that muted. So we can actually do it. You'll see that I'll tear the balance so that the balance will actually read 0. And then as we start to put current through the magnet or current through the wire, as we've got 0.3, 0.5, now all of a sudden we got 1.5 amps. Now you can see that we're actually getting a magnetic field around my wire that's pushing down because those two magnetic fields are repelling, and you can actually measure it on a scale. So you can actually verify that, yes, you are creating a magnetic field. So you've got a couple of those videos where we've done that demonstration. I have the NASA representation for the magnetic field. And I believe that many of you discovered this when you were going out to look at your comparison of the magnetic field that you measured with using your cell phone and being able to look at the magnetic field here. Then you've got the field calculator at the Earth's surface, and you can actually go in, put in your coordinates, and be able to see what the magnitude of the magnetic field is. And this, again, I think many of you discovered this as you were doing your laboratory, which is one of the reasons why I have you do that laboratory. So you can actually see what the magnetic field is at your area. And there are pictures and maps of those. Here's the magnetic field charts that you can get out through NOAA as well. And they do the model, and you can actually go in and look at there's the magnetic world model chart released, and you can see the various magnetic fields. And one of these will actually follow how the wobble of magnetic north has been moving over time as you've been going through it. So you can get various interesting things about what the Earth is doing associated with it. And then finally, I like to show this one. I do my space weather. and I actually watch it and monitor it. You can actually set it up on your phone so that you can look at whether or not we're going to get a solar flare that will cause an aurora. But you can see that for the last 3 years, we've always had sunspots, and we've got a big sunspot currently facing us right now. And you can actually see those sunspots on there. And yet they take lots of different pictures. You can get the chromosphere, you can see the aurora oval, you can go to the Fairbanks, Alaska, be able to look at our auroras. And we've actually seen auroras as far south as Texas over the last 2 years on a couple of very big solar magnetic storms that have come our way. So that brings those charged particles in there. So this is a fun site to go in and look at. We also use SLU, and we can actually take pictures of the sun using the SLU camera or the SLU telescopes that we have as part of our astronomy program. And we have a heliostat over in Enid so that we can actually track sunspots with using the heliostat as part of the research as well. So that's kind of an aspect of looking at our magnetic field. So let's kind of talk through some of the general things about a magnetic field, because this is, again, very much like what we did with Coulomb, and we looked at and developed Coulomb's law based off of observations. We have a number of observations that we deal with when we're associating with our magnetic fields. All right, so hopefully everybody's played with magnets. And some interesting things about magnets is if I have a north and a south pole, and I have a north and a north pole, these are going to actually repel. We also know that if I do a magnet with my north and south pole, we actually can use iron filings and be able to see our magnetic fields around our bar magnets. And we can look at those bar magnets. And as you guys have seen, you can use magnetometers and actually measure the magnetic field. And we can draw magnetic field lines just like we can draw electric field lines. And as we just pointed out, the Earth is a great big magnet, and that's what allows us to have, as if I do my Earth here, and we're on our wobble, and we have our magnetic field, that was, we get those, as those charged particles come in, they're going to come in at the poles, and that's what's going to produce our various auroras, that will get those auroras that we get, whether we do it as the magnetic fields go in here. So the force, which we just saw, and we saw that in that demonstration, we get an interesting thing that happens. So one thing is that we're going to represent our magnetic fields using a ray. And if I do X's, I'm going to produce my magnetic field into the paper. So think about these being the feathers on my arrow. And if I'm coming out of the paper, I'm going to represent my magnetic field as dots. So this is into the paper, and this is out of the paper. Because one of the things that we see is if I take a charged particle and I put it into a magnetic field, my charged particle is going to rotate. And we're going to see something that's a little different. We're going to use our right-hand rule again. Because if I'm looking at my magnetic field, one of the observations that we see is that my charged particle actually is going to move in my magnetic field going in that direction. And we're going to have to use our right hand rule to get that. So our force is proportional to the charge that we have, the speed of the charge, and our magnetic field. And we know that it's maximum when I'm perpendicular. I get that maximum when I'm perpendicular, so we can actually write that the force is equal to my charge times the velocity times the strength of my magnetic field sine of the angle. And B is going to be the magnitude of my magnetic field, which is going to be the force Q V sine of my angle. And B is going to be measured in Tesla, or you might also see it measured in Gauss. And 1 Tesla is 10 to the 4 Gauss. So 1 Tesla is a very large number in terms of magnetic field. Your MRIs and things are very different. You're not going to be getting something on the order of Teslas. You get them on the order of Gausses, but not necessarily on the order of Teslas. So let's review the right-hand rule, okay? So if I'm looking at my right-hand rule, the force that's going to cause my charge to move, this is going to be my force. And here's my magnetic field. Here is the velocity. And we're going to use my right hand as I'm going from my velocity to my magnetic field that gets my force out of the paper. So this is your magnetic field. This is our angle, and we get our force coming out of the paper.
And
so
our thumb is the force.
Your thumb is the force.
Okay, so we just point that in the direction of whichever way the force is pointing.
Yeah, that's when we're going to end up using it to figure out current. For example, what we're going to find is, so if I have a wire and I've got current going into my wire, I'm going to, because that's, think about what your force is doing. Your force is making your charge move. So that's going to give you your current. So I'm going to put my thumb along the direction of the current, assuming it's positive, because remember, Ben Franklin gave it to us backwards. So if that's the case, then my magnetic field is going to be into the paper on this side. And my magnetic field will come out of the paper on that side. Because what we see and what Ampere showed is if I have current going through my wire, I can put little compasses here and you can actually see the magnetic field with my compass as it goes around my wire. So we're going to go from velocity to the magnetic field, gives me my force out of the paper, but we're going to end up using it more with current. And so my thumb is along the wire and it's going into the paper so that we get that magnetic field. So what this does for us really, and I'm really not going to go into a whole lot tonight because I know you guys are working on your test and I want to give you guys a chance to do that and get the things that are working on there, is that if we deal with a GC mass spectrometer, what happens to that is that we'll get our charged particles will go in, and because of the strength of the magnetic field, it's going to curve over and hit a detector. And depending on the mass of that, it'll hit the detector a little differently. And in fact, we call this a radius that we actually use. And that radius is equal to the mass times the velocity divided by the magnitude of the charge times the magnetic field. And that's what we refer to as our radius, or our cyclotron radius, that allows us to do things like GC mass spec, allows us to do a variety of other instruments. And this gives us our idea of how our charges are going to move. And as I said, our charges are going to follow our magnetic field and actually will move in a spiral as we go down and along our magnetic field. All right. So we're going to stop there because I know people have their tests that are working, but I wanted to show you everything that we had, give you some demonstrations so that you could actually see it. And then we'll start calculating magnetic fields from wires tomorrow. Questions? Oh, I got somebody in chat. Hang on. Actually, we don't have any labs this week. You finished up your magnetic field lab last week. You did your Ohm's law lab last week, and our optics labs are next week. So we really don't have a lab this week. I got discombobulated on terms of labs.
On number 12 on the test, it says what is the difference between electric field and electric potential? Are you okay with it just being like a kind of like a T-chart?
That would be fine. Yeah.
Okay. I'm trying to see if I've got any other questions besides you just giving me the answers.
I understand.